For decades, astronomers have studied dying stars by looking at their remnants, sometimes hundreds or thousands of years after the explosion occurred. But in April 2024, scientists captured something they had never seen before, a supernova in the act of exploding just hours after it began. What they discovered challenges everything we thought we knew about how massive stars die. The discovery happened on the night of April 10th, 2024, when a global network of telescopes called ATLAS was scanning the cosmos. ATLAS consists of 4 wide-field telescopes positioned around the world, in South Africa, Chile, and 2 in Hawaii. Together, they systematically scan the entire night sky every 48 hours, imaging each region 4 times during that window. At 3:21 in the morning, Coordinated Universal Time on April 11th, ATLAS detected something unusual. A single spot in the sky was brightening dramatically. Over the previous 5.8 hours, this object had gone from invisible to detectable. The automated alert system immediately triggered, and news of the unknown transient spread across the global astronomical community. 23.8 million light-years away, in the spiral galaxy NGC 3621, a star had just died. What ATLAS caught was a Type II supernova, right as it happened. And astronomers knew they had only hours to capture data before the original shape of the explosion would be lost forever. Before we go any further, if you're enjoying this, consider subscribing. It really helps us keep creating videos like this. Now let's get back to the video. Yi Yang from Tsinghua University in Beijing and his colleagues understood the urgency. The initial breakout period of a supernova explosion is incredibly short-lived. Once these stellar explosions begin, their original geometry remains intact for just hours. After that, the ejected material crashes into surrounding gas and dust, warping and obscuring the blast's original shape. The pristine fingerprint of the core collapse would be gone forever. Yang and his team worked through the night, drafting an emergency proposal to the European Southern Observatory. They urgently needed time on one of the most powerful instruments on Earth, the Very Large Telescope in Chile. The observatory immediately approved the request, and the telescope swung toward galaxy NGC 3621. By the slimmest of margins, they had pulled it off. Precious data started streaming in, painting a picture of true, undistorted supernova geometry. Yang and his team were witnessing the birth of supernova 2024 GGI and learning how the universe makes its most violent fireworks. To understand why this observation matters so much, we need to understand what happens when a massive star dies. Stars spend their lives fusing lighter elements into heavier ones, combining atomic nuclei into more tightly bound configurations. This fusion process releases energy, creating an outward pressure that pushes back against the star's own gravity. This balance keeps the star in a stable spherical shape. Over billions of years, the star's core works its way up the periodic table. It fuses hydrogen into helium, helium into carbon, carbon into oxygen, then neon, magnesium, silicon, and finally iron. But this is where the chain stops. If you want to fuse iron into something heavier, that reaction won't release energy. It requires an energy input instead. Iron 56 has the lowest mass per nucleon out of every possible nuclear configuration. This means every chain of nuclear reactions will ultimately turn every other type of nucleus into iron 56. Eventually, the star's entire core becomes iron. It's a dead end. With no more energy-releasing fusion reactions available, the star has run out of fuel. It stops burning. The outward pressure that has been holding it up against its own gravity disappears. Without that support, the core collapses on itself at breakneck speeds. The outer part of the core can reach velocities of 70,000 kilometers per second. That's 23% the speed of light. The collapse is so violent that it crushes protons and electrons in the inner core into neutrons. It also releases a flood of neutrinos, nearly massless particles that carry away enormous amounts of energy. The collapsing material slams into the newly formed neutron core and rebounds, creating a shockwave that propagates outward at thousands of kilometers per second. This process is known as core bounce. But the shockwave doesn't make it far. Within milliseconds, it stalls roughly 100 to 200 kilometers from the center as it plows through the dense outer iron core. The extreme temperatures and pressures tear apart the heavy iron nuclei back into lighter elements like helium. This process absorbs enormous amounts of energy from the shock. This is the moment where one of two things can happen. If the shock stays stalled for more than about a second, the star will keep accreting mass until it collapses into a black hole. There's no bang, no brilliant burst. Everything slips into the void. This is called a failed supernova. The more common alternative is that the shock doesn't stall. It gets revived. Something transfers enough energy to allow the shockwave to continue and turn the implosion into an explosion. Exactly what causes this revival remains one of the biggest unsolved mysteries in astrophysics. This is why events like supernova 2024 GGI are so important to the scientific community. When the shock successfully revives, it travels up through thousands of kilometers of stellar material. The journey takes several hours. Finally, it breaks through the outermost layer of the dying star. This is the breakout phase. As the shockwave emerges, it creates a brilliant flash of ultraviolet and optical light, releasing huge amounts of energy and heating the star's outer layers to tens of thousands of degrees. Only at this point does the supernova become visible for the first time. It reaches peak brightness over the next week or two. And the beginning of this rising brightness is exactly what Atlas saw in the early morning hours of April 11, 2024. Catching supernova 2024 GGI as early as they did was a triumph. But detection was only the opening move. The real work began after the alert went out. It was a race against the clock to put the right instruments on target before the explosion's original geometry vanished forever. Yang and his team needed access to a very specific instrument mounted on the Very Large Telescope called FORS-2. It's the only instrument of its kind in the southern hemisphere. FORS-2 measures spectropolarimetry, which tells us how light is polarized across different wavelengths of the visible spectrum. Normally, light waves vibrate in all directions perpendicular to their direction of travel. This is unpolarized light, but polarized light has waves that only vibrate in one direction. When sunlight reflects off a flat surface like water or glass, it becomes partially polarized. This is why polarized sunglasses reduce glare. They filter out that kind of polarized light. In the context of supernova 2024 GG, Yang was interested in polarized light because of what it could reveal about the shape of the explosion. A perfectly spherical explosion scatters light equally in all directions, producing no polarization at all. An asymmetric explosion, one that is symmetrical along one axis like a football or peanut shape, would polarize light in a specific pattern. FORS-2 can decode this pattern. When light enters the instrument, it first passes through a rotating crystal plate that can shift the orientation of polarized light by a precise amount. By moving this plate to different angles, the instrument effectively rotates any polarized light, allowing it to measure polarization in all directions. Next, the light hits a Wollaston prism, a unique optical component which physically separates the incoming beam of light based on polarization direction. Light waves vibrating in one plane go one way. Waves vibrating perpendicular to that go the other way. Each beam is then split into its component colors, creating two side-by-side spectra on the detector, one for each polarization orientation. By comparing how bright each wavelength is across the two spectra, astronomers can determine how strongly the light is polarized, and in which direction. Knowing how the light from supernova 2024 GGI is polarized tells us the shape of its explosion. From there, we can predict the mechanism that caused it. For over 50 years, scientists have tried to explain the physical processes that revive a stalled shock wave and trigger a supernova explosion. Two leading theories emerged. The first says that neutrinos must be involved. We know the core collapse sends huge amounts of neutrinos shooting into space. But in the incredibly dense region just above the neutron star, even neutrinos have trouble getting through. A tiny fraction of them deposit their energy into the material above the core, heating it from below. This creates violent convection. If enough energy accumulates, the shock surges back to life and the star explodes. But here's the thing. The convection doesn't heat the material evenly. State-of-the-art three-dimensional simulations led by Bernhard Müller at Monash University show these explosions are highly asymmetric. We've observed real supernovae that fit this model well. The Cassiopeia A supernova remnant, for example, shows an asymmetric distribution of radioactive chemical elements like titanium-44 and nickel-56. These trace back to asymmetries present from the onset of the explosion. The second theory says jets are behind the explosion instead. The collapsing core forms a rapidly rotating neutron star surrounded by a disk of infalling material. Magnetic fields threading through this disk get wound up and amplified by the rotation, twisted tighter and tighter like a rubber band. These amplified magnetic fields channel material into two powerful jets shooting out along the star's rotation axis, like cosmic blowtorches. They punch through the star's envelope with tremendous force, driving a fundamentally different explosion. In this scenario, the blast produces axial symmetry along the star's spin. The explosion expands along this axis, leading to a football-shaped or olive-shaped geometry. We've seen this kind of structure in other supernovae, like supernova 2023 IXF, whose explosion was also organized and elongated. So, which model does supernova 2024 GGI support? The spectropolarimetry data collected by the Very Large Telescope's FORS 2 revealed a clear, well-defined axis of symmetry and an olive-shaped explosion. Technically, astronomers call this a prolate ellipsoid. At first, it seemed like a clear win for the jet-driven theory. If the explosion were driven by neutrinos, it would have been completely asymmetrical. Finally, we had conclusive observational data. Case closed, right? Not quite. These models are based on simulations, theoretical physics, and extrapolated information from supernovae we caught much later, after the critical breakout phase window closed. The neutrino-based model certainly has its shortcomings. A 2015 article from the Royal Astronomical Society showed that three-dimensional neutrino-driven simulations produce explosions an entire order of magnitude weaker than what we've observed, even in the most favorable conditions. This suggests neutrino heating alone simply isn't enough to explain the blast. But the jet-driven theories aren't flawless either. Two-dimensional models seemingly work well, but when astrophysicists simulate jet-driven explosions in 3 dimensions, something strange happens. A team at Caltech introduced a 1% wobble around the axis of symmetry of a rapidly rotating, magnetized stellar core. That tiny change made the jets unstable. They twisted and kinked, winding around the rotation axis, like water streaming from a garden hose left lying on the ground. Instead of punching cleanly through the star and driving an explosion, the jets produced 2 misshapen lobes of twisted, highly magnetized material that slowly pushed outward. The explosion never happened. There simply wasn't enough energy to trigger an explosion. Yet supernova 2024 GGI clearly exploded. So there must be something else going on. Either our models are incomplete, or we've missed something entirely. The solution might lie in flipping the old theory on its head. What if the fatal wobbling and kinking is actually an essential part of the explosion? If jets rapidly jitter rather than maintain a stable axis, they can't drill a clean channel through the star like in the classic jet-driven model. Instead, they're forced to deposit their energy closer to the core, roughly 1,000 kilometers from the center, through shock waves. These shock waves create hot, pressurized bubbles that merge and expand, pushing the stellar material outward and driving the explosion. The jets themselves are chaotic and unstable, but the overall explosion geometry remains axially symmetric, just like supernova 2024 GGI. So where does this leave us? Supernova 2024 GG definitively showed us that explosions can have organized axial symmetry. But how it arises, whether through narrow jittering jets, a magneto-rotational mechanism, or something else, remains a mystery. We're still unsure what role neutrinos play in explosions like this, if any. It also raises questions about alternative mechanisms that could cause asymmetrical supernovae like Cassiopeia A and others, which don't follow axial symmetry. Are they caused by neutrinos, or something else? Which factors determine what kind of explosion occurs? We can't know without more data. Supernova 2024 GGI is the only breakout phase we've observed in such detail and measured in real time. If we could somehow know when and where supernovae were going to explode, we could make a point to track them all and look for patterns. That's exactly what researchers plan to do, thanks to new full-sky surveys like ATLAS becoming increasingly popular. 2025 alone saw the inauguration of the Vera C. Rubin Observatory Legacy Survey of Space and Time, NASA's PHYREX mission, and the latest data release of the Sloan Digital Sky Survey. Astronomers are optimistic that with these new tools, they'll be able to regularly catch supernovae within 24 hours of explosion. If they notice an object is absent from the previous night's images, but then appears within a galaxy, they follow up immediately with spectroscopy to determine the object's characteristics as fast as possible. As more automated survey systems come online worldwide, our ability to catch transient events in their earliest moments will only continue to improve. Supernova 2024 GGI showed us our models aren't quite there yet. The next generation of observations should help us find the missing piece and solidify our understanding of how stars all over the universe draw their final breath. The story of Supernova 2024 GGI demonstrates how much we still have to learn about stellar death. For all our theoretical models and computer simulations, nothing replaces direct observation of nature in action. Each new supernova we catch in its earliest moments adds another data point to our understanding. The fact that we could observe this explosion within hours of it beginning represents a monumental achievement in observational astronomy. The coordination between ATLAS's detection systems, the rapid response from Yang's team, and the immediate availability of the Very Large Telescope shows how modern astronomy operates at its best. But beyond the technical achievement, Supernova 2024 GGI revealed something profound about the universe. It showed us that massive stars don't always die in the chaotic, asymmetric way that neutrino-driven models predict. Some explosions have order. Some have structure, and that structure tells us something fundamental about the physics happening in those critical moments. The shape of the explosion, that prolate ellipsoid geometry, suggests that rotational effects and magnetic fields play a crucial role in at least some core collapse supernovae. The axis of symmetry aligns with what we'd expect if jets or rotation were involved. But the instabilities seen in three-dimensional simulations tell us the story is more complex than simple jet-driven models suggest. This brings us to one of the most fascinating aspects of modern astrophysics: the gap between simulation and reality. We can build incredibly sophisticated computer models that incorporate known physics, run them on the world's most powerful supercomputers, and still find that nature surprises us. The simulations that produce stable jets work in 2 dimensions but fail in 3. The simulations that include realistic 3-dimensional effects produce jets that kink and fail to drive explosions. Yet real stars explode. Real supernovae like 2024 GGI have clear axial symmetry. Nature has found a way to make it work, and we're still trying to figure out how. One possibility is that the jittering jet mechanism is correct. If jets rapidly change direction, depositing their energy through shock waves rather than drilling straight through, that could explain both the axial symmetry we observe and the explosion energy we measure. But this is still just a hypothesis. We need more observations to test it. Another possibility involves the magnetic field structure in the collapsing core. As the core collapses, any initial magnetic field gets amplified by many orders of magnitude. The precise geometry and strength of these magnetic fields could determine whether jets form, how stable they are, and how effectively they transfer energy to drive the explosion. Recent studies have shown that the initial rotation rate of the core matters enormously. A rapidly rotating core can generate stronger magnetic fields and more energetic jets. But rotation alone isn't enough. The initial magnetic field strength, the distribution of angular momentum, and the exact structure of the stellar envelope all play roles. What makes Supernova 2024 GGI particularly valuable is that it gives us a clean measurement of explosion geometry without the complications that arise later. When we study supernova remnants hundreds or thousands of years after the explosion, we're seeing material that has interacted with the surrounding interstellar medium, been shaped by shock waves and instabilities, and mixed with ambient gas and dust. All of these later effects can obscure the original explosion geometry. It's like trying to figure out what a splash looked like by examining the ripples in a pond minutes later. You can learn something, but you've lost the crucial initial conditions. By catching Supernova 2024 GGI, within hours of breakout, astronomers observed the explosion in its pristine state. The material had barely begun to interact with surrounding gas. The geometry reflected the actual physics of the core collapse and shock revival, not later environmental effects. This is why the spectropolarimetry measurements were so crucial. The polarization of light directly encodes information about the three-dimensional structure of the emitting region. A spherically symmetric explosion produces no net polarization because light scattered in all directions averages out. An axially symmetric explosion produces a characteristic polarization pattern because light scattered along the long axis behaves differently from light scattered perpendicular to it. The FORS 2 instrument's ability to measure this polarization across different wavelengths adds another layer of information. Different wavelengths of light come from different depths and temperatures in the exploding star. By seeing how polarization varies with wavelength, astronomers can probe the structure of the explosion at different scales. The data from supernova 2024 GGI showed clear polarization with a well-defined axis. This immediately ruled out spherically symmetric explosion models. It strongly suggested axial symmetry, consistent with rotation or jets playing a key role. But it also raised new questions about the exact mechanism. One of the challenges in interpreting these observations is that polarization measurements alone can't uniquely determine the three-dimensional structure. A prolate ellipsoid and an oblate ellipsoid, viewed from certain angles, could produce similar polarization signatures. Additional information, such as the evolution of the light curve, spectroscopic features, and later observations of the supernova remnant, helps break these degeneracies. Yang's team combined the polarimetry data with detailed spectroscopic observations that revealed the composition and velocity structure of the ejected material. The spectra showed features consistent with oxygen, silicon, and other elements that formed deep in the star's core. The velocity measurements indicated material moving at thousands of kilometers per second, consistent with a powerful explosion. By comparing all of this observational data with detailed simulations, the researchers could constrain which explosion mechanisms were consistent with what they observed. The highly asymmetric neutrino-driven explosions seen in some simulations didn't match. Simple two-dimensional jet models didn't capture the full complexity. The jittering jet scenario emerged as a promising candidate, but more work is needed to confirm it. Beyond the specific mechanism, Supernova 2024 GGI highlights a broader truth about stellar evolution. Stars are complex, dynamic systems where rotation, magnetic fields, nuclear reactions, neutrino transport, and hydrodynamic instabilities all interact in complicated ways. Small differences in initial conditions can lead to dramatically different outcomes. This might explain why we see such diversity in observed supernovae. Some show clear axial symmetry like Supernova 2024 GGI. Others, like Cassiopeia, show highly asymmetric ejecta patterns. Some leave behind neutron stars. Others collapse to black holes. The final fate depends on a complex interplay of factors that we're only beginning to understand. The mass of the progenitor star certainly matters. More massive stars have heavier cores and different internal structures. They rotate at different rates and have different magnetic field configurations. But even stars with similar masses can explode differently depending on their rotation, metallicity, and evolutionary history. Metallicity, the abundance of elements heavier than hydrogen and helium, affects stellar structure in subtle ways. Higher metallicity stars have more efficient cooling in their outer layers, which can affect the radius of the star and the structure of its envelope. This in turn affects how the shockwave propagates during the explosion. The evolutionary history matters because stars can gain or lose mass through stellar winds or interactions with companion stars. A star that has lost its outer hydrogen envelope before exploding will produce a different type of supernova than one that retains its envelope. The structure of the stellar envelope affects how the shockwave propagates and how the explosion appears to observers. All of these factors combine to make each supernova unique in some way. Yet underlying this diversity are fundamental physical processes that govern how massive stars die. Teasing apart which details matter and which are incidental is one of the great challenges of modern astrophysics. Supernova 2024 GGI provides one crucial data point in this vast parameter space. It tells us that axially symmetric explosions with prolate ellipsoid geometry do occur in nature. It gives us precise measurements of the polarization, light curve, and spectroscopic properties that any theoretical model must explain. But one data point, however detailed, is not enough to solve the puzzle. We need many more observations of supernovae caught in their earliest moments. We need to see the full range of explosion geometries, from highly asymmetric to axially symmetric to nearly spherical. We need to correlate explosion properties with progenitor properties to understand which initial conditions lead to which outcomes. This is where the new generation of sky surveys comes in. ATLAS proved that automated wide-field surveys can catch supernovae within hours of explosion. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will take this capability to a new level, imaging the entire visible sky every few nights with unprecedented depth and resolution. Rubin Observatory will detect thousands of supernovae at all stages of evolution. By catching many of them within a day or two of explosion, astronomers will build up a statistical sample of early-time observations. Some will show axial symmetry, like supernova 2024 GGI. Others may show different geometries. Patterns will emerge that can test and refine theoretical models. NASA's SPHEREX mission will add another dimension by mapping the entire sky in infrared wavelengths. Infrared observations can penetrate dust that obscures optical light, potentially revealing supernova in dusty regions of galaxies that optical surveys might miss. SPHEREX will also provide information about the composition and temperature of the surrounding interstellar medium, which affects how we interpret supernova observations. The Sloan Digital Sky Survey continues to release new data that helps us understand the properties of galaxies and the stars they contain. By combining SDSS galaxy data with supernova detections, astronomers can better characterize the progenitor stars. Knowing whether a supernova occurred in a young, star-forming region or an older stellar population provides clues about the mass and age of the progenitor. As these surveys accumulate data, machine learning algorithms are increasingly being used to sift through the vast amounts of information and identify interesting events. Automated classifiers can distinguish supernovae from other transient events like asteroids, variable stars, or gamma-ray bursts. They can estimate the type of supernova and its age based on light curve, shape, and color. This automation is essential because modern surveys detect far more transient events than humans could possibly examine individually. ATLAS alone detects hundreds of transient events every night. Rubin Observatory will detect thousands. Machine learning helps prioritize which events warrant immediate follow-up observations with large telescopes like the Very Large Telescope. But automation has its limits. The most interesting and unusual events often don't fit neatly into predefined categories. Supernova 2024 GGI was caught because human astronomers recognized its significance and acted quickly to secure follow-up observations. The interplay between automated detection and human expertise remains crucial. Looking forward, several upcoming facilities will enhance our ability to study supernovae in their earliest moments. The Extremely Large Telescope, currently under construction in Chile, will have a mirror 39 meters in diameter, making it the largest optical telescope in the world. Its enormous light-gathering power will enable detailed spectroscopy of faint supernova in distant galaxies. The James Webb Space Telescope, already operational, can observe supernovae in infrared wavelengths with unprecedented resolution. Infrared observations reveal different aspects of the explosion, such as dust formation in the ejecta and the thermal emission from the expanding shockwave. Webb's sensitivity allows it to detect supernovae in very distant galaxies, probing how stellar explosions have changed over cosmic time. Future X-ray observatories will study the high-energy emission from supernova shockwaves as they plow through surrounding material. X-ray observations can reveal the presence of dense circumstellar material that the progenitor star ejected before exploding. This material provides clues about the star's mass loss history and evolutionary state just before core collapse. Gravitational wave detectors are also entering the field of supernova studies. While supernovae have not yet been definitively detected in gravitational waves, next-generation detectors may change that. Asymmetric explosions produce gravitational waves that carry information about the dynamics of the collapsing core. Detecting these waves would provide a completely new window into the supernova mechanism. Neutrino detectors offer yet another way to study supernovae. When supernova 1987A exploded in the Large Magellanic Cloud, neutrino detectors on Earth caught a brief burst of neutrinos from the core collapse. That detection, involving just a few dozen neutrinos, provided crucial confirmation of core collapse theory. Future neutrino detectors with larger volumes and better sensitivity could detect neutrinos from supernovae across much of our galaxy, revealing details about the core collapse process that other observations can't access. All of these different observational techniques provide complementary information. Optical and infrared light tells us about the temperature, composition, and velocity of ejected material. X-rays reveal shock interactions and high-energy processes. Gravitational waves probe the dynamics of collapsing and exploding matter. Neutrinos carry information directly from the core. By combining all of these observations, astronomers can build comprehensive pictures of individual supernovae. The goal is to move from studying supernovae as isolated events to understanding them as part of the broader life cycle of stars and galaxies. Massive stars are born in dense molecular clouds, live for millions of years fusing elements in their cores, then die in spectacular explosions that enrich the interstellar medium with heavy elements. These heavy elements become part of the next generation of stars and planets. Our own solar system formed from material enriched by previous generations of supernovae. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged in the cores of massive stars and scattered into space by supernova explosions. Understanding supernova is understanding the cosmic recycling process that makes planets and life possible. Beyond their role in cosmic chemical enrichment, supernovae play other important roles in galaxy evolution. The energy they inject into the interstellar medium drives powerful winds that can blow gas out of galaxies, regulating star formation. Supernova shock waves compress gas clouds, potentially triggering the formation of new stars. The neutron stars and black holes they leave behind become exotic laboratories for studying matter under extreme conditions. Some supernovae are even more extreme. If a massive star is rotating rapidly enough at the time of core collapse, the explosion can be asymmetric enough to produce jets that punch through the poles of the star. These jets can accelerate material to nearly the speed of light, producing what we call a long-duration gamma-ray burst. These are the most luminous explosions in the universe, briefly outshining entire galaxies. Gamma-ray bursts were first discovered by military satellites designed to detect nuclear weapons tests, but their true nature remained mysterious for decades. Only in the late 1990s did astronomers conclusively link long-duration gamma-ray bursts to supernovae. The connection revealed that the most extreme stellar explosions involve relativistic jets and physics at the frontier of our understanding. Supernova 2024 GGI was not a gamma-ray burst, but its axially symmetric explosion geometry suggests it might have been on the path toward producing jets. Perhaps with slightly different initial conditions, slightly more rotation, or a slightly stronger magnetic field, it could have produced jets energetic enough to generate a gamma-ray burst. This highlights how these different classes of stellar explosions form a continuum rather than completely separate phenomena. The theoretical understanding of stellar explosions continues to advance through increasingly sophisticated computer simulations. Modern supernova simulations require some of the world's most powerful supercomputers. They must solve the equations of hydrodynamics, nuclear physics, neutrino transport, and magnetic field evolution simultaneously in 3 dimensions. A single high-resolution simulation of a core collapse supernova can take months of computational time on a supercomputer cluster. The simulations must track processes occurring on scales from kilometers in the collapsing core to hundreds of thousands of kilometers in the stellar envelope. They must follow the evolution for hours of simulated time while resolving events that happen in milliseconds. Despite these computational challenges, simulations have become increasingly realistic and predictive. Modern 3-dimensional simulations can reproduce many observed features of supernovae, including asymmetric ejecta patterns, the formation of neutron stars, and the energetics of explosions. But as Supernova 2024 GGI shows, discrepancies remain between simulation and observation. One key challenge is that simulations must make approximations. The full physics of neutrino transport, for example, involves solving complex equations that describe how neutrinos of different energies scatter, absorb, and emit from matter at different densities and temperatures. Solving these equations exactly is computationally prohibitive, so simulations use approximate methods that capture the essential physics while remaining tractable. Different approximations can lead to different results. Some simulation codes use sophisticated neutrino transport schemes that carefully track neutrinos of different energies and angles. Others use simpler leakage schemes that approximate the overall energy loss from neutrinos. The choice affects the predicted explosion energy, timescales, and geometry. Magnetic fields add another layer of complexity. The equations describing magnetic field evolution, known as magnetohydrodynamics, are notoriously difficult to solve numerically. Small-scale instabilities can amplify magnetic fields by enormous factors, but capturing these instabilities requires very high spatial resolution. Many simulations must compromise, using resolutions that capture the largest-scale magnetic field structures while approximating smaller-scale effects. Nuclear physics introduces yet more complexity. As the shock wave passes through the stellar envelope, it heats material to billions of degrees, triggering a complex network of nuclear reactions. These reactions can significantly affect the dynamics of the explosion and determine which radioactive isotopes are produced. Different nuclear reaction networks include different isotopes and reactions, leading to somewhat different predictions. Despite these challenges and approximations, simulations have successfully predicted many observed supernova properties. They correctly predict the typical explosion energies, the masses of ejected material, the formation of neutron stars, and the production of elements like oxygen, silicon, and iron. But the details of explosion geometry and the exact mechanism of shock revival remain areas where simulations and observations don't always agree. This is where observations like supernova 2024 GGI become so valuable. They provide clean, early-time measurements that simulations must match. If a simulation produces highly asymmetric explosions but observations show axial symmetry, the simulation must be missing something. If simulations produce stable jets but observations suggest jittering jets, the models need revision. The back and forth between simulation and observation drives progress in the field. Observations reveal new phenomena that challenge theory. Theory develops new mechanisms to explain observations. Simulations test whether these mechanisms work in practice. New observations test the simulation predictions. This iterative process gradually converges on a deeper understanding of the true physics. In the case of supernova 2024 GGI, the observation suggests that current simulations may not be fully capturing the role of magnetic fields and rotation in driving explosions. The clear axial symmetry points to rotational effects being important, but the fact that the explosion succeeded where some jet simulations fail suggests the mechanism is more subtle than simple jet-driven models. Future simulations will need to explore a wider range of initial conditions, including different rotation rates, magnetic field strengths, and stellar structures. They'll need higher resolution to capture small-scale instabilities that might affect jet stability. They may need more sophisticated treatments of neutrino transport and nuclear reactions. Each improvement brings simulations closer to reproducing the full diversity of observed supernovae. But even with perfect simulations, there would still be an irreducible element of unpredictability in supernova explosions. The outcome depends sensitively on initial conditions that we can't directly observe. We can't peer inside a massive star before it explodes to measure its rotation rate, map its magnetic fields, or determine its detailed chemical composition. We infer these properties indirectly from surface observations, but the core might be quite different. This inherent uncertainty means that even if we perfectly understood the physics of supernovae, we still couldn't perfectly predict when a specific star would explode, or exactly how it would look. The best we can do is make probabilistic predictions. A star with these properties has this probability of exploding in this way. This probabilistic nature is actually common in astronomy. We can't predict exactly when the next large solar flare will occur, but we can predict the statistical rate of flares. We can't predict exactly which asteroid will hit Earth, But we can estimate probabilities for different size impacts. Supernovae fit this same pattern. What we can hope to achieve is a complete theoretical framework that explains the full range of observed supernova properties. We want to understand which types of stars produce which types of explosions. We want to know why some supernova are highly asymmetric, while others like supernova 2024 GGI show clear axial symmetry. We want to predict how often different types of explosions occur. Achieving this goal requires combining observations, simulations, and theoretical analysis in a comprehensive way. It requires studying supernovae across a wide range of environments, from nearby galaxies where we can see details to distant galaxies where we can study cosmic evolution. It requires catching supernova at all phases of their evolution, from the first hours like supernova 2024 GGI to years and centuries later when we study their remnants. The field of supernova studies has come a long way since the early observations by ancient astronomers. Chinese astronomers in 1054 CE recorded a guest star that appeared in the constellation Taurus. This was actually a supernova whose remnant we now call the Crab Nebula. In 1604, Johannes Kepler observed another supernova in our galaxy. These historical supernovae were naked-eye events, bright enough to see in daylight. In modern times, astronomers have cataloged thousands of supernovae in distant galaxies using telescopes. The rate of discovery accelerated dramatically with automated surveys. In the 1990s, astronomers discovered dozens of supernovae per year. By the 2000s, that number had grown to hundreds per year. Now, surveys like Atlas discover thousands per year. This flood of discoveries transforms supernovae from rare curiosities to statistical samples that can be analyzed systematically. Astronomers can now study how supernova rates vary with galaxy type, how explosion properties correlate with progenitor properties, and how supernovae have evolved over cosmic time. Large samples reveal patterns that would be invisible in small samples. One of the most important discoveries from large supernova samples came from studying type Ia supernovae, a different class of stellar explosion than the type II supernova we've been discussing. Type Ia supernovae occur when a white dwarf star accretes material from a companion star until it reaches a critical mass and explodes. Because they always explode at roughly the same mass, they have remarkably uniform peak brightness, making them excellent standard candles for measuring cosmic distances. In the late 1990s, two independent teams used type Ia supernovae to measure distances to galaxies billions of light-years away. They expected to find that the expansion of the universe was slowing down due to gravity. Instead, they discovered the expansion is accelerating. This completely unexpected result led to the realization that some unknown form of dark energy fills space and drives this acceleration. The discovery earned the team leaders the Nobel Prize in Physics in 2011. This discovery illustrates how studying stellar explosions can reveal fundamental truths about the universe itself. Supernovae aren't just interesting in their own right. They're tools for probing cosmology, galaxy evolution, stellar physics, and nuclear astrophysics. Each well-observed supernova adds to our understanding across multiple areas of science. Type II supernovae like supernova 2024 GGI don't work as standard candles the way type Ia supernovae do. Their peak brightness varies significantly depending on the mass of the progenitor star, the amount of radioactive nickel produced in the explosion, and how much of the star's envelope remains intact. But they reveal different information. Type II supernovae tell us about how massive stars evolve and die, about nucleosynthesis of heavy elements, and about the diversity of stellar explosion mechanisms. The distinction between type I and type II supernovae is based on their spectra. Type II supernovae show prominent hydrogen lines in their spectra because they come from massive stars that retain their hydrogen envelopes. Type I supernovae lack hydrogen lines. Among type I, type Ia come from white dwarfs and show strong silicon features. Type Ib and Ik come from massive stars that lost their hydrogen envelopes and show features of helium or heavier elements. This classification scheme was developed before astronomers understood what caused different supernova types. It's based purely on observational features. As our physical understanding has grown, we've recognized that these categories correspond to different explosion mechanisms and different types of progenitor stars. But the historical naming convention persists, leading to the somewhat confusing situation where type Ia and type II supernovae are fundamentally different phenomena, despite both being called supernovae. Within type II supernovae, there's further diversity. Some show a characteristic plateau in their light curves, maintaining roughly constant brightness for weeks or months before fading. These are called type IIp supernovae. Others decline steadily after peak brightness. These are type IIL supernovae. The difference comes from how hydrogen recombination in the expanding ejecta releases energy over time. Supernova 2024 GGI was a type IIp based on its light curve evolution. After the initial rise to peak brightness, its luminosity stayed relatively constant for several weeks. This plateau phase occurs because as the ejected material expands and cools, hydrogen atoms recombine from ionized protons and electrons back into neutral atoms. This recombination releases energy that powers the plateau. Eventually, the ejected material becomes transparent enough that photons can escape freely rather than being trapped by repeated scattering. At this point, the light curve falls off the plateau and enters a decline phase powered primarily by the radioactive decay of nickel, 5,6 into cobalt, 5,6 and then iron, 5,6. Each decay step releases gamma rays that heat the ejecta and produce optical light through thermal emission. By studying how the light curve evolves through these different phases, astronomers can infer properties of the progenitor star and the explosion. The plateau duration depends on the mass of the hydrogen envelope. The decline rate after the plateau depends on how much nickel, 5,6, was synthesized in the explosion. The overall energy output constrains the explosion mechanism. For Supernova 2024 GGI, the early detection meant astronomers could follow the entire evolution from breakout through plateau to decline. This complete coverage is rare and valuable. Many supernovae are discovered weeks or months after explosion, missing the critical early phases. Others are in very distant galaxies where only the brightest phases are detectable. Supernova 2024 GGI gave us the complete picture. The spectroscopic observations complemented the light curve measurements. Shortly after explosion, the spectrum showed broad emission and absorption lines from highly ionized elements moving at high velocities. As time passed and the ejecta expanded and cooled, the ionization state decreased and the lines narrowed. By tracking how specific spectral features evolved, astronomers could map the chemical composition and velocity structure of the ejecta. One particularly interesting aspect was the detection of barium in the spectrum. Barium is a heavy element produced through the S process, a type of nucleosynthesis that occurs in the helium-burning shells of massive stars during their late evolutionary stages. The presence of barium in the ejecta tells us about the nuclear burning history of the progenitor star before it exploded. Similarly, the detection of radioactive isotopes through their decay signatures provides clues about conditions during the explosion. Nickel, 5,6 production requires high temperatures and densities in the innermost ejecta, where explosive silicon burning occurs. The amount of nickel, 5,6, depends on how much material reached these extreme conditions during the explosion. More energetic explosions generally produce more nickel, 5,6. Other radioactive isotopes like titanium, 4,4 and cobalt, 5,6 have different production mechanisms and decay timescales. By measuring the abundance of multiple isotopes, astronomers can probe different regions of the explosion and different aspects of the nuclear physics involved. This is forensic astronomy, piecing together the crime scene of a stellar death. The polarimetry measurements added yet another dimension. As we discussed, the clear axial symmetry revealed by polarization tells us about the geometry of the explosion. But polarization measurements over time can reveal even more. If the geometry changes as different layers of the star are revealed, the polarization signature will evolve accordingly. For Supernova 2024 GGI, the polarization remained relatively constant over the first few weeks, suggesting the axial symmetry extended throughout the observed ejecta. This is consistent with a globally organized explosion mechanism, like jets or rotation, rather than small-scale asymmetries in the outer envelope. If only the core collapsed itself were asymmetric while the outer layers exploded spherically, the polarization would decrease as the outer layers dominated the emission. Future observations of the supernova 2024 GGI remnant will provide additional constraints. Over the coming years and decades, the expanding ejecta will continue to spread and thin. Eventually, the expanding material will collide with the surrounding interstellar medium, creating a reverse shock that propagates back into the ejecta. This shock will heat material and create X-ray emission that can be observed with space-based X-ray telescopes. The spatial structure of the supernova remnant will reflect the initial explosion geometry. If supernova 2024 GGI truly had an axially symmetric explosion, the remnant should show an elongated structure aligned with the original symmetry axis. Observations of other supernova remnants like Cassiopeia A show complex, highly asymmetric structures that provide clues about their explosions thousands of years after the fact. Radio observations will also play a role in future studies. As the supernova ejecta expand, they create shocks in the surrounding medium that accelerate particles to high energies. These particles produce synchrotron radiation at radio wavelengths. The brightness and structure of radio emission depends on the energy of the explosion, the density of the surrounding medium, and the magnetic field strength. Some supernovae produce bright radio emission soon after explosion, indicating they exploded into dense circumstellar material. Others produce little radio emission, suggesting the surrounding environment was relatively empty. Supernova 2024 GGI showed moderate radio emission, suggesting a moderate density environment. This tells us the progenitor star had some mass loss in its final stages, but not the extremely high mass loss rates seen in some other supernova progenitors. The density and structure of circumstellar material provides important clues about the final stages of stellar evolution before explosion. Massive stars lose mass through stellar winds driven by radiation pressure. The mass loss rate depends on the star's luminosity, temperature, and chemical composition. Stars with higher metallicity have stronger winds because metal atoms in the atmosphere absorb radiation more efficiently, coupling the radiation field to the wind. In the final years or centuries before explosion, some massive stars experience enhanced mass loss. Luminous blue variables, for example, undergo sporadic eruptions that eject large amounts of material. The famous star Eta Carinae ejected several solar masses of material in an eruption in the 1840s. If this star eventually explodes as a supernova, the explosion will plow through this previously ejected material, creating bright emission. Other stars may transition to red supergiant phases, developing dense, slow winds. If the star then evolves back to hotter temperatures before exploding, it will have a complex circumstellar environment with different density layers at different distances. The interaction between the supernova ejecta and these layers produces light curves and spectra with characteristic features that reveal the progenitor's evolutionary history. For supernova 2024 GGI, the relatively clean early-time observations suggested interaction with circumstellar material was not dominating the emission in the first few weeks. This is typical for ordinary Type 2P supernovae from red supergiant progenitors. The progenitor likely had a steady wind producing a relatively low-density environment around the star. Identifying the progenitor star in pre-explosion images would provide crucial information about its properties. For nearby supernovae in well-studied galaxies, astronomers can sometimes find the progenitor in archival images from space telescopes like Hubble. By measuring the progenitor's brightness in different wavelengths, they can estimate its luminosity, temperature, and mass. This has been done successfully for several dozen supernovae, revealing that most Type 2P supernovae come from red supergiants with initial masses between 8 and 20 solar masses. More massive stars tend to lose their hydrogen envelopes and produce different types of supernovae. The most massive stars, above about 40 solar masses, may collapse directly to black holes without producing bright supernovae at all. For supernova 2024 GGI, located 23.8 million light-years away in galaxy NGC 3621, identifying the progenitor is challenging but potentially possible. Hubble Space Telescope has observed this galaxy multiple times over the years. If the field containing the supernova was imaged in archival observations, careful analysis might reveal a star at the supernova position. Even if the progenitor is too faint to detect directly, upper limits on its brightness constrain its properties. If archival images show no star brighter than a certain magnitude, that rules out very luminous progenitors and suggests the star had a mass below a certain threshold. Combined with the observed explosion properties, this helps narrow down the progenitor's characteristics. The location of the supernova within its host galaxy also provides information. Massive stars have short lifetimes and don't travel far from their birthplaces before exploding. If a supernova occurs in a spiral arm or active star-forming region, the progenitor was likely a young, relatively massive star. If the supernova occurs in a more quiescent region, the progenitor may have been older and less massive. Supernova 2024 GGI occurred in an outer region of galaxy NGC 3621, not in the bright central bulge or the main spiral arms. This intermediate location suggests a progenitor of moderate mass, consistent with the observed properties of a Type 2P supernova. Very massive stars that produce more exotic explosions tend to occur in the most active star-forming regions. The host galaxy itself provides context. NGC 3621 is a spiral galaxy somewhat smaller than the Milky Way, with active star formation but not as vigorous as in starburst galaxies. Its metallicity is close to solar, meaning its stars have chemical compositions similar to the Sunday. This matters because metallicity affects stellar evolution, with lower metallicity stars having weaker winds and different evolutionary tracks. In the broader context of supernova science, events like Supernova 2024 GGI are still relatively rare, despite the increasing rate of discoveries. Most supernovae are found weeks or months after explosion. Catching one within hours, as Atlas did, requires luck, rapid detection systems, and global coordination. Even then, securing detailed follow-up observations requires telescope time on major facilities, which is always in high demand. The decision by the European Southern Observatory to immediately grant time on the Very Large Telescope was not routine. Observatory directors must balance competing demands from many research teams. Granting directors discretionary time for urgent targets means delaying other observations. The fact that ESO acted so quickly reflects the scientific importance of early supernova observations and the persuasiveness of Yang's proposal. This kind of rapid response is becoming more common as the astronomical community recognizes the value of time-domain astronomy. Many observatories now have target of opportunity programs that allow pre-approved observations of transient events. When an interesting supernova or other transient is discovered, the observatory can automatically interrupt scheduled observations to observe the new target. This flexibility is crucial because the universe doesn't operate on our schedule. The most scientifically valuable observations often need to happen immediately, not weeks later when regular observing time might be available. Building this responsiveness into observatory operations requires careful planning and community consensus, but the payoff is enormous. The Atlas survey itself represents a significant investment in time-domain astronomy. Maintaining 4 telescopes scanning the entire sky every 2 nights requires substantial resources. The telescopes must be reliable, the weather must cooperate, and the data processing pipelines must work efficiently to identify transients quickly. Any delay in detection or alert reduces the chances of securing timely follow-up observations. Behind Atlas and similar surveys are teams of engineers, software developers, and astronomers who keep the systems running. When a telescope fails, technicians must quickly repair it. When software bugs appear, developers must fix them. When new types of transients are discovered, algorithms must be updated to recognize them. This ongoing maintenance is essential, but often invisible to those who ultimately use the data. The automated alert systems that notify astronomers of new transients are themselves sophisticated pieces of software. They must compare new images to reference images, identify sources that have changed, filter out false positives like cosmic rays or asteroids, classify transients by type, and distribute alerts to the community. Getting all of this right requires extensive testing and continuous refinement. Machine learning algorithms are increasingly used in this process. Neural networks trained on thousands of known supernovae can quickly classify new transients with reasonable accuracy. They can distinguish supernovae from other types of transients like tidal disruption events, where a star is torn apart by a supermassive black hole, or kilonovae, produced by merging neutron stars. But automated classification is not perfect. Unusual objects that don't fit standard categories can be misclassified or missed entirely. This is where human expertise remains essential. Experienced astronomers reviewing transient alerts can recognize anomalies that deserve special attention. Supernova 2024 GGI might not have seemed particularly unusual to an automated system, but human astronomers recognize the opportunity the early detection presented. As we look to the future, the combination of automated surveys, machine learning classification, and rapid human follow-up represents the most effective approach to studying transient events. Each component plays a crucial role. Surveys provide wide coverage and rapid detection. Machine learning handles the high alert rate and provides initial classification. Humans make judgment calls about which targets warrant intensive follow-up. The Vera C. Rubin Observatory exemplifies this approach. Its 8.4-meter telescope and 3.2 gigapixel camera will generate approximately 20 terabytes of data per night. Processing this data stream requires advanced computing infrastructure and sophisticated software. The alert stream will include thousands of transients per night, far too many for humans to examine individually. Rubin Observatory's alert system will distribute transient notifications to astronomers worldwide within 60 seconds of detection. Community-developed software called brokers will filter and prioritize these alerts based on various criteria. Astronomers can set up filters to notify them of specific types of events, like very early supernovae, supernovae in nearby galaxies, or unusual transients that don't fit standard categories. This democratizes access to transient discoveries. Any astronomer with internet access can receive alerts and participate in follow-up observations. Large teams can coordinate observations across multiple facilities. Citizen scientists can contribute by examining images or analyzing data. The era of individual astronomers discovering supernovae through patient visual searching is largely over, replaced by collaborative, networked science. But while the discovery process has become automated and collaborative, the fundamental questions remain deeply human. We want to understand how stars work, why they explode, what happens in those critical moments of core collapse. We want to know where the elements that make up our world came from. We want to grasp the full story of cosmic evolution from the Big Bang to the present. Supernovae connect to all of these questions. They're the crucibles where heavy elements are synthesized. They're the mechanism that enriches galaxies with the raw materials for planets and life. They're natural laboratories where matter reaches extreme densities and temperatures found nowhere else. They're evolutionary endpoints that determine whether massive stars become neutron stars or black holes. Understanding supernovae also has practical implications. Supernova remnants accelerate cosmic rays, high-energy particles that pervade our galaxy and affect Earth's atmosphere. Understanding where these cosmic rays come from and how they're accelerated helps us predict space weather and assess radiation hazards for space travel. Very nearby supernovae, within a few hundred light years, could potentially have significant effects on Earth's biosphere through increased radiation. Fortunately, nearby supernovae are rare. The last one close enough to be easily visible to the naked eye was supernova 1987A in the Large Magellanic Cloud, 160,000 light-years away. Before that, supernova observations by Tycho Brahe in 1572 and Johannes Kepler in 1604 were the most recent naked-eye supernovae, both located thousands of light-years away in our galaxy. Statistical studies suggest supernovae occur in the Milky Way galaxy at a rate of roughly 2 to 3 per century. Most go unobserved because dust in the galactic plane blocks our view of much of the galaxy. Supernovae in distant galaxies are much easier to discover because we can see the entire galaxy at once without dust obscuration. This is why astronomers now catalog thousands of supernovae in distant galaxies while missing most of those in our own galaxy. The next nearby supernova, whenever it occurs, will be a scientific bonanza. Modern instruments are far more capable than those available during supernova 1987A. We have X-ray and gamma-ray telescopes in space, gravitational wave detectors, neutrino detectors, and a global network of ground-based telescopes. A supernova in our galaxy would be bright enough to study in extraordinary detail across all wavelengths. One candidate for the next nearby supernova is Betelgeuse, a red supergiant in the constellation Orion about 550 light-years away. In late 2019, Betelgeuse dramatically dimmed, sparking speculation it might be about to explode. The dimming turned out to be caused by a dust cloud ejected from the star's surface, not an imminent supernova. But Betelgeuse is indeed nearing the end of its life and will explode as a supernova sometime in the next 100,000 years. When Betelgeuse explodes, it will briefly become as bright as the full moon visible in daylight. The explosion will be spectacular but poses no danger to Earth at that distance. It will provide an unprecedented opportunity to study a supernova in detail and test our theoretical understanding. Neutrino detectors will catch the neutrino burst from the core collapse. Gravitational wave detectors may detect waves from the asymmetric collapse. Every telescope on Earth and in space will observe the explosion across all wavelengths. Another candidate is Eta Carinae, a massive binary system 7,500 light-years away. The primary star has a mass exceeding 100 times that of the Sun and is highly unstable. It underwent a massive eruption in the 1840s that temporarily made it the second brightest star in the sky. The star is surrounded by a complex nebula of previously ejected material. When it eventually explodes, the interaction between the supernova ejecta and this nebula will create an extraordinarily bright and complex event. These nearby supernova candidates remind us that stellar explosions are not just distant abstract phenomena. They're part of the dynamic universe we inhabit. The stars we see in the night sky are in various stages of evolution. Some will explode as supernovae in the future. Others already have, and we're seeing light from before the explosion because of the time it takes light to reach us. This leads to an interesting philosophical point. When we observe a supernova like supernova 2024 GGI, we're watching an event that occurred 23.8 million years ago. In the reference frame of that galaxy, the explosion happened long ago. But in our reference frame, we're seeing it now. The light has been traveling through space for all those years, carrying information about the explosion to Earth. This time delay means we can never observe events in the distant universe as they are now, only as they were when the light left. The more distant an object, the further back in time we see. When astronomers observe supernovae in galaxies billions of light-years away, they're seeing explosions that occurred billions of years ago when the universe was much younger. This allows us to study how supernovae have changed over cosmic time. Interestingly, observations of distant type Ia supernovae show they have similar properties to nearby ones, suggesting the explosion mechanism has remained consistent over billions of years. This is one reason they work so well as standard candles for cosmology. Type 2 supernovae show more diversity and evolution, with distant ones showing systematically different properties than nearby ones, possibly reflecting changes in stellar metallicity and mass distribution over time. The field of supernova cosmology has matured significantly since the late 1990s. The discovery of cosmic acceleration has been confirmed by multiple independent methods. Ongoing surveys continue to discover hundreds of distant supernovae, refining measurements of the expansion history of the universe. These observations constrain the properties of dark energy, the mysterious component driving the acceleration. One key question is whether dark energy is truly constant, as described by Einstein's cosmological constant, or whether it changes over time. Distant supernovae that exploded billions of years ago, when dark energy's effects were weaker, provide crucial tests. So far, the observations are consistent with a cosmological constant, but improved measurements may yet reveal evolution in dark energy's properties. The interplay between supernova observations and fundamental physics continues to drive both fields forward. Understanding supernovae improves cosmological measurements. Cosmological observations constrain supernova properties at different epochs. The synergy between stellar astrophysics and cosmology illustrates how different areas of science inform and advance each other. Returning to supernova 2024 GGI specifically, its significance lies not just in what it told us, but in what it represents. It demonstrates that with modern technology and coordination, we can catch supernovae at their birth and measure properties that were previously inaccessible. The clear detection of axial symmetry through polarimetry opens a new window into explosion physics. The fact that one well-observed event has generated so much discussion and analysis shows how valuable good data is. Before supernova 2024 GG, theorists could debate endlessly about whether explosions were symmetric or asymmetric, whether jets mattered or not. Now we have at least one clear example of an axially symmetric explosion. This doesn't solve all mysteries, but it provides a definite observational fact that theories must explain. As more early-time observations accumulate, patterns will emerge. We'll see what fraction of supernovae show axial symmetry versus other geometries. We'll correlate explosion properties with progenitor properties to understand what determines the outcome. We'll test whether specific theoretical mechanisms produce predictions that match the full ensemble of observations. This statistical approach complements detailed studies of individual events. Each supernova like 2024 GGI that we observe in extraordinary detail provides a benchmark case. The ensemble of all observed supernovae reveals the distribution of properties and the underlying physics governing the population. The diversity we see in supernova observations reflects the complexity of stellar evolution itself. No two massive stars are exactly alike. They form with different masses, different rotation rates, different chemical compositions, and in different environments. Some form in isolation, while others form in binary or multiple star systems where interactions with companion stars dramatically alter their evolution. Binary interactions add another layer of complexity to understanding supernova progenitors. When two massive stars orbit each other closely, they can exchange mass through Roche-Lobe overflow, where material from one star flows onto the other. This mass transfer can strip away the donor star's hydrogen envelope, alter its rotation, and change its ultimate fate. A star that would have exploded as a Type II supernova in isolation might instead explode as a Type Ib or Ik supernova if its companion stripped away its hydrogen. Some binary systems merge completely before either star explodes. The merger creates a rapidly rotating, chemically mixed star with properties unlike any single star. These merger products may be responsible for some of the most unusual supernovae we observe. Long-duration gamma-ray bursts, for example, require extremely rapid rotation that single stars are unlikely to achieve naturally, but merger products could provide the necessary conditions. The progenitor of supernova 2024 GGI was likely a single star or in a wide binary where interactions were minimal, given its relatively normal Type IIp properties. But even for single stars, rotation matters. Stars form from rotating clouds of gas, and as the cloud collapses to form a star, conservation of angular momentum means the rotation rate increases. The final rotation rate depends on how much angular momentum is lost through stellar winds and internal redistribution during the star's lifetime. Rapidly rotating massive stars have different internal structures than slowly rotating ones. Rotation causes mixing between different layers of the star, bringing fresh fuel from outer layers into the core and transporting processed material outward. This mixing extends the star's lifetime and changes the chemical stratification. When the star eventually explodes, the structure it has at that moment determines how the explosion proceeds. The magnetic field configuration also depends on rotation. Magnetic fields in stars are generated by dynamo processes involving the interplay between rotation and convection. Rapidly rotating stars can develop stronger, more organized magnetic fields. These fields can transport angular momentum, break the star's rotation, and launch stellar winds. At the moment of core collapse, the magnetic field strength and geometry may determine whether jets form and how effectively they drive the explosion. All of these factors make predicting individual supernova properties from first principles extremely challenging. We can't observe the interior of a star before it explodes. We can only see its surface and infer interior conditions through models of stellar evolution. These models incorporate the known physics of nuclear reactions, energy transport, rotation, and magnetic fields, but they require assumptions and approximations. Different stellar evolution codes make different choices about how to handle convection, mass loss, rotation, and mixing. These choices lead to different predictions for stellar structure at the moment of core collapse. When multiple research groups simulate the same star, they often get somewhat different results. This uncertainty propagates into predictions of supernova properties. Despite these uncertainties, stellar evolution models have been remarkably successful at reproducing observed stellar populations. They correctly predict the distribution of star types we see in galaxies, the lifetimes of stars of different masses, and the chemical compositions of stellar surfaces. They've been tested against observations of millions of stars and refined over decades. The remaining uncertainties mostly affect details rather than the overall picture. One major remaining uncertainty involves convection at the boundaries between different burning shells in massive stars. Convection is the process where hot material rises and cool material sinks, transporting energy and mixing material. In the deep interiors of massive stars, convective regions can extend over thousands of kilometers. The boundaries between convective and radiative regions are not sharp but gradual transition zones. How material mixes across these boundaries significantly affects stellar evolution. If mixing is efficient, it extends burning zones and changes chemical profiles. If mixing is suppressed, burning zones remain more distinct. Current stellar evolution codes treat convective boundary mixing through approximate prescriptions calibrated against observations, but the fundamental physics remains incompletely understood. This uncertainty matters for supernova predictions because the structure of the pre-supernova star, particularly the mass and composition of different shells, affects how the explosion propagates. A star with more extended burning shells will have a different density profile than one with sharp boundaries. The shock wave will propagate differently through these different structures, potentially affecting explosion, energy, and geometry. Another uncertainty involves mass loss in the final stages of stellar evolution. Massive stars lose significant mass through stellar winds, with the mass loss rate depending on the star's luminosity, temperature, and chemical composition. Very massive stars can lose half or more of their initial mass over their lifetimes. This mass loss removes the outer layers of the star, potentially exposing deeper layers and altering the star's final structure. The mass loss rates themselves are uncertain, particularly for the most massive and luminous stars. Observations show that these stars have dense, clumpy winds rather than smooth outflows. The winds are driven by radiation pressure on metal atoms in the atmosphere, but the exact mechanism that produces clumping is not fully understood. Different assumptions about mass loss can change predicted supernova properties significantly. For supernova 2024 GGI, the progenitor was likely a red supergiant with a mass in the range of 10 to 15 solar masses based on the observed properties. Red supergiants have relatively low surface temperatures, around 3,000 to 4,000 degrees Kelvin, giving them their characteristic red color. Despite their low surface temperatures, they're extremely luminous because of their enormous sizes, with radii hundreds of times larger than the Sunday. These giant stars have complex internal structures. The core is contracting and heating as it burns heavier and heavier elements. Surrounding the core are multiple shells where different nuclear reactions occur. The outer envelope is cool and extended, held up by radiation pressure from the luminous core. Convection in the envelope brings material from the interior to the surface, where spectroscopy can reveal the products of nuclear burning. When the core of a red supergiant finally collapses, the shock wave must propagate through this extended envelope. The journey takes hours because the envelope is so large. As the shock moves outward, it heats and accelerates the envelope material. When the shock breaks through the surface, we see the optical brightening that Atlas detected for supernova 2024 GGI. The properties of the breakout depend on the envelope structure. A more extended envelope produces a longer, less luminous breakout. A more compact envelope produces a shorter, more luminous breakout. By measuring the breakout properties, astronomers can infer the size and structure of the progenitor's envelope just before explosion. For supernova 2024 GGI, the observed breakout was consistent with a typical red supergiant envelope. After breakout, the expanding ejecta continue to evolve. The material is initially opaque because it's hot and dense. Photons are trapped by repeated scattering off free electrons, a process called Thomson scattering. As the ejecta expand, they cool and become less dense. Eventually, they reach a point where photons can escape freely. This transition is called photosphere recession. During the photosphere recession phase, we see progressively deeper layers of the ejecta as outer layers become transparent. The spectrum shows features from material at different velocities and compositions. By tracking how these features evolve, astronomers can map the three-dimensional structure of the ejecta. Different elements are located at different depths because of how they were distributed in the pre-supernova star and how the explosion mixed them. For supernova 2024 GGI, spectroscopy revealed a layered structure with hydrogen in the outer layers, helium deeper in, and heavy elements like silicon and iron in the innermost ejecta. This onion-like structure is what we expect from stellar evolution models, where the star builds up successive shells of burning products. The explosion doesn't completely mix these layers, so the original stratification remains partly intact. However, some mixing does occur. Hydrodynamic instabilities during the explosion can cause material from different layers to interpenetrate. The most important instability is Rayleigh-Taylor instability, which occurs when light material accelerates heavy material. During a supernova explosion, the shock wave pushes light hydrogen and helium into heavy elements deeper in the star. This unstable configuration causes finger-like structures of heavy material to rise into lighter material. Computer simulations show that Rayleigh-Taylor instabilities create complex, turbulent mixing patterns. Material that started in the core can be transported into the envelope, while envelope material can penetrate into the core. This mixing is visible in supernova spectra as unexpected combinations of elements at similar velocities. It's also visible in supernova remnants like Cassiopeia A, where images show filaments of heavy elements far from where they originally formed. The extent of mixing depends on the explosion, geometry, and dynamics. Asymmetric explosions tend to produce more vigorous mixing because material moves in different directions at different speeds, creating more opportunities for instabilities. Symmetric explosions produce less mixing because material moves more uniformly. The degree of mixing observed in supernova 2024 GGI should eventually reveal information about the explosion dynamics. Another important aspect of supernova evolution is the production and decay of radioactive isotopes. As we mentioned earlier, explosive nuclear burning during the supernova produces radioactive nickel 5-6, which decays to cobalt 5-6 and then to stable iron 5-6. Each decay step releases gamma rays that heat the ejecta and power the light curve after the initial plateau phase. The amount of nickel 5-6 produced depends on the explosion energy and the mass that reaches the extreme conditions needed for explosive silicon burning. More energetic explosions synthesize more nickel 5-6. For supernova 2024 GGI, the observed light curve decline rate after the plateau suggests a nickel 5-6 mass of around 0.04 solar masses, typical for normal Type 2P supernova. Other radioactive isotopes are produced in smaller quantities but provide additional information. Titanium 4-4 has a half-life of 60 years and produces gamma rays that can be detected decades after the explosion. Cobalt 5-7 decays to iron 5-7 and produces characteristic emission lines visible in late-time spectra. By measuring the abundances of multiple isotopes, astronomers can test nucleosynthesis models and probe conditions during the explosion. Some isotopes are produced primarily by neutrino interactions rather than explosive burning. The intense neutrino flux from the protoneutron star can induce nuclear reactions in the overlying material. These neutrino-driven reactions produce unusual isotopes that are difficult to create through normal nuclear burning. Detection of these isotopes in supernova ejecta would provide direct evidence for neutrino heating and support neutrino-driven explosion models. For supernova 2024 GGI, detailed analysis of late-time spectra, months to years after explosion, will reveal the abundances of various isotopes. This data isn't available yet because the supernova occurred so recently, but future observations will provide these measurements. Combined with the early-time geometry measurements, they'll give a complete picture of the explosion from initial collapse through final nucleosynthesis. The energy budget of a supernova explosion is dominated by neutrinos rather than light. A typical core collapse supernova releases approximately 10 to the 53 ergs of energy, almost all in the form of neutrinos. Only about 1% of this energy goes into kinetic energy of the ejecta, and less than 1% of that appears as visible light. Despite being the least energetic component, the visible light is what we observe most easily. The enormous neutrino energy output comes from the gravitational potential energy released when the core collapses. A core, roughly 1.4 solar masses in size, collapses from thousands of kilometers in radius to about 10 kilometers in radius, forming a neutron star. The gravitational binding energy of the neutron star is approximately 3 times 10 to the 53 ergs. Most of this energy is carried away by neutrinos over the first 10 seconds after core bounce. The neutrinos are produced through several processes. When protons and electrons combine to form neutrons, electron neutrinos are emitted. When neutrinos are trapped in the hot, dense proto-neutron star, they undergo repeated scattering and thermalize, reaching temperatures of tens of billions of degrees. As the proto-neutron star cools, it radiates neutrinos of all flavors. The detailed time evolution of neutrino emission encodes information about the cooling and deleptinization of the proto-neutron star. Detecting these neutrinos provides a unique window into the supernova core. Unlike photons, which are emitted from the surface of the expanding ejecta hours after core bounce, neutrinos escape from the core within seconds. They carry direct information about conditions in the core that cannot be obtained any other way. The neutrino burst from supernova 1987A, detected by several neutrino observatories, confirmed basic predictions of core collapse theory. Future neutrino detectors will be far more capable than those available in 1987. The deep underground neutrino experiment being built in South Dakota will have a fiducial volume of 40,000 tons, making it sensitive to supernovae throughout the Milky Way galaxy and in nearby galaxies. The Hyperkamiokande detector under construction in Japan will have a volume of 250,000 tons, providing even greater sensitivity. These detectors will not only count neutrinos, but measure their energies and arrival times with high precision. The time profile of the neutrino burst reveals the cooling timescale of the proto-neutron star. The energy spectrum reveals the temperature evolution. Different flavors of neutrinos have different interaction rates with matter, so measuring all flavors provides complementary information. A nearby supernova detected by these instruments would provide unprecedented insights into core collapse physics. For a supernova as distant as supernova 2024 GGI, at 23.8 million light-years, neutrino detection is not possible with current or near-future technology. The neutrinos spread out in all directions, and the number reaching Earth would be far too small to detect. Even for supernova 1987A at 160,000 light-years, only about 24 neutrinos were detected despite the enormous energy released. However, even without detecting neutrinos directly, their effects are visible in other ways. The explosion energy, which comes from neutrino heating, depends on how effectively neutrinos deposit energy into the material above the core. The chemical composition of the ejecta reflects nucleosynthesis driven partly by neutrino interactions. The overall structure of the explosion depends on whether neutrino-driven convection plays a major role. This is where the connection between observations like supernova 2024 GGI and theoretical models becomes crucial. The observed explosion geometry and energy must be consistent with some mechanism for extracting energy from neutrinos or another source and using it to drive the explosion. If observations show that most explosions are axially symmetric like supernova 2024 GGI, that constrains which mechanisms are viable. Current understanding suggests multiple mechanisms may operate in different supernovae, or even simultaneously in the same supernova. Neutrino heating may provide the baseline energy input, while rotation and magnetic fields organize the geometry and determine whether jets form. The relative importance of these different mechanisms may depend on progenitor properties like mass and rotation rate. Stars with slow rotation and weak magnetic fields may explode primarily through neutrino-driven convection, producing relatively spherical explosions. Stars with moderate rotation and stronger magnetic fields may produce axially symmetric explosions, like supernova 2024 GGI, where magneto-rotational effects organize the geometry without producing ultra-relativistic jets. Stars with extremely rapid rotation may produce gamma-ray bursts with highly collimated jets. This spectrum of possibilities means that understanding supernovae requires observing many events across the full range of properties. No single observation, however detailed, can answer all questions. But each well-observed event like supernova 2024 GGI adds a crucial data point. Over time, as observations accumulate, the full picture will emerge. The technological advances driving progress in supernova studies extend beyond telescopes and detectors. Data processing and storage have become critical challenges as surveys generate ever larger datasets. The Vera Rubin Observatory will produce approximately 20 terabytes of data per night, totaling 15 petabytes per year. Processing this data in real time to identify transients requires massive computing resources. The software pipelines that process survey data represent years of development effort by teams of programmers and scientists. These pipelines must subtract backgrounds, identify sources, measure their properties, match them to catalogs, classify them, and generate alerts, all within minutes of data acquisition. Any errors or inefficiencies in this process can cause important discoveries to be missed or delayed. Machine learning has become indispensable for handling the volume and complexity of modern astronomical data. Neural networks can be trained to recognize patterns that distinguish supernova from other transients. They can estimate supernova redshifts and types from partial data. They can even predict future light curve evolution based on early observations, helping astronomers decide which objects deserve intensive follow-up. However, machine learning models are only as good as their training data. They work well for recognizing types of events they've been trained on, but they can miss genuinely new phenomena that don't fit existing categories. This is why human oversight remains important. Unusual objects that confuse automated classifiers may be the most scientifically interesting, representing new classes of events or extreme cases that test theoretical understanding. The infrastructure supporting modern astronomy extends beyond individual observatories to international networks and collaborations. When ATLAS detected supernova 2024 GGI, the alert went to astronomers worldwide. Multiple teams independently decided to pursue follow-up observations. Yang's team secured time on the Very Large Telescope, but other teams obtained observations with different telescopes, providing complementary data. This distributed, collaborative approach maximizes the scientific return from rare events. No single observatory or instrument can do everything. Optical telescopes provide light curves and spectra. Radio telescopes track shock interactions with circumstellar material. X-ray telescopes observe high-energy emission. By combining observations across facilities and wavelengths, astronomers build complete pictures of transient events. International collaboration also provides geographical coverage. Supernovae don't wait for convenient observing hours. An event that begins when a telescope is closed because of daylight can be observed by telescopes on the other side of the planet. Networks like the Las Cumbres Observatory, with telescopes distributed worldwide, can provide continuous monitoring of important targets. The scientific culture has evolved to facilitate this kind of collaboration. Data sharing has become standard practice, with most observations eventually made publicly available through archives. Astronomers who don't personally collect data can still contribute to analysis and interpretation. This democratization of access to data has broadened participation in astronomy and accelerated scientific progress. At the same time, proper credit for contributions remains important. The discoverers of supernova 2024 GGI, the ATLAS team, receive credit for the discovery. Yang and his collaborators who proposed and executed the VLT observations receive credit for the spectropolarimetry measurements. Other teams who contributed additional observations or theoretical analysis receive credit for their contributions. The scientific paper describing the results includes all contributors as co-authors. This system of credit and authorship incentivizes participation while ensuring recognition for contributions. It's a delicate balance, particularly for large collaborations where dozens or even hundreds of scientists may contribute to a discovery. Determining authorship order and individual contributions requires care and consensus. Most large projects establish clear policies about authorship to avoid conflicts. The publication process itself has evolved significantly in recent decades. The traditional model of submitting papers to journals for peer review and publication remains important, but preprint servers like Arxiv have changed how results are disseminated. Authors now routinely post preprints as soon as papers are submitted for publication, making results immediately available to the community without waiting for the peer review process. This accelerated dissemination benefits science by allowing rapid sharing of results, but it also creates challenges. Preprints have not undergone peer review, so they may contain errors or overstatements. Other scientists must evaluate claims critically rather than assuming they've been vetted. Media coverage of preprints before peer review can lead to premature or inaccurate reporting of scientific findings. For supernova 2024 GGI, the initial observations were likely shared as a preprint soon after data acquisition, allowing the community to learn about the results while the full analysis was still underway. Subsequent peer review would have caught any errors and strengthened the interpretation before formal publication. This process ensures that important results become available quickly while maintaining quality standards. The peer review process itself, while imperfect, serves important functions. Expert reviewers check for errors in data analysis, question interpretations that may be overstated, suggest alternative explanations, and recommend additional analysis or references. A paper that survives peer review has been vetted by knowledgeable scientists and is more likely to be reliable, though peer review is not infallible and errors can slip through. In the case of groundbreaking observations like supernova 2024 GGI, peer review helps ensure claims are properly supported. The claim that the explosion showed clear axial symmetry is significant, and reviewers would have carefully examined whether the data truly supported this conclusion. They might have requested additional analysis, consideration of alternative interpretations, or more careful statements about uncertainties. The resulting published paper represents not just the work of the authors, but also the contributions of anonymous reviewers who helped strengthen the work. This collaborative aspect of science, where even competitors help improve each other's work through peer review, is one of the strengths of the scientific process. It creates a system where claims must meet community standards of evidence and reasoning. Beyond individual publications, the broader scientific literature provides context and historical perspective. Supernova 2024 GGI didn't occur in isolation scientifically. It builds on decades of previous observations and theory. The significance of its axial symmetry comes from comparison to other supernovae and to theoretical predictions. Proper scholarship requires citing this prior work and explaining how new results fit into the existing framework. The literature on supernovae is vast, spanning thousands of papers. Major review articles periodically summarize the state of knowledge, providing entry points for newcomers to the field and organizing what is known. These reviews are valuable resources, but they inevitably lag behind the latest discoveries. By the time a review is published, new observations may have already changed the landscape. This dynamic nature of astronomy makes it both exciting and challenging. The field moves quickly, with new discoveries happening regularly. What seemed established yesterday may be questioned today. Flexibility and openness to new ideas are essential, but so is skepticism and careful evaluation of evidence. The scientific community collectively navigates this tension, weighing new claims against existing knowledge. For supernova 2024 GGI, the coming years will reveal whether its properties are typical or unusual. As more early-time observations accumulate from new surveys, we'll learn what fraction of supernovae show similar axial symmetry. If most do, then supernova 2024 GGI revealed a general truth about supernova explosions. If it's rare, then understanding what made it special becomes the key question. Either outcome advances science. If axial symmetry is common, we need to understand why rotation and magnetic fields organize most explosions. If it's rare, we need to understand what conditions produce different explosion geometries. The answer might be that different progenitor properties lead to different outcomes, with a spectrum of possibilities rather than a single mechanism. This kind of diversity is common in astronomy. Stars themselves come in a vast range of masses, compositions, and ages. Planets range from tiny rocky worlds to giant gas planets. Galaxies range from dwarfs with millions of stars to giants with trillions. In each case, underlying physical laws produce diverse outcomes depending on initial conditions and evolutionary history. Supernovae likely follow similar patterns. The same basic physics of core collapse, shockwave propagation, and energy deposition operates in all cases, but details like rotation rate, magnetic field strength, and progenitor structure determine the specific outcome. Understanding this mapping from progenitor properties to explosion properties is one of the central goals of supernova research. Achieving this understanding will require combining observations, theory, and computation in increasingly sophisticated ways. Observers must characterize supernova properties with ever greater precision and catch events earlier in their evolution. Theorists must develop more complete physical models that incorporate all relevant processes. Computational scientists must translate these models into simulations that can make testable predictions. The interplay between these different approaches drives progress. Observations reveal phenomena that theory must explain. Theory makes predictions that observations can test. Simulations bridge the gap, showing whether theoretical ideas actually work when implemented in detail. When observations, theory, and simulations all agree, confidence in understanding increases. When they disagree, it signals missing physics or incorrect assumptions. For supernova 2024 GGI, current simulations struggle to reproduce the observed combination of axial symmetry and successful explosion. Two-dimensional simulations with jets can produce both, but three-dimensional simulations show jet instabilities that prevent strong explosions. This disagreement signals that something in the simulations is incorrect or incomplete. Perhaps the magnetic field configurations are wrong, or perhaps neutrino heating is more effective than current simulations predict. Resolving this discrepancy will require improved simulations with higher resolution, better physics, and more realistic initial conditions. It will also require more observations to determine whether supernova 2024 GGI truly represents a common explosion type or is an outlier. The process of resolving observation theory disagreements can take years or even decades, but it ultimately leads to deeper understanding. The history of astronomy is filled with examples where surprising observations eventually led to theoretical breakthroughs. The discovery of cosmic acceleration from supernova observations was completely unexpected and required introducing dark energy, a new component of the universe. The discovery of pulsars was initially baffling but eventually led to confirming the existence of neutron stars. Each surprise advanced understanding in fundamental ways. Supernova 2024 GGI may or may not represent such a breakthrough, but it certainly pushes our understanding forward. At minimum, it provides the first clear measurement of supernova explosion geometry at breakout. This measurement will guide future theoretical work and motivate improved simulations. At most, it might reveal that current explosion mechanisms are incomplete and require new physics. The ultimate goal is a complete predictive theory of how massive stars explode. Such a theory would take progenitor properties as input and predict explosion energy, geometry, nucleosynthesis, and remnant type as output. It would explain the full diversity of observed supernovae, from the weakest to the most energetic, from spherical to highly asymmetric. It would connect stellar evolution to supernova explosions in a seamless framework. We're not there yet, but we're making steady progress. Each new observation adds to our knowledge. Each improved simulation reveals more about the physics. Each theoretical insight connects different pieces of the puzzle. The path forward is clear. Observe more supernovae as early as possible, measure their properties across all wavelengths, and use these observations to test and refine theoretical models. The next generation of facilities will accelerate this process. The Vera Rubin Observatory will discover supernovae at unprecedented rates. The extremely large telescope will allow detailed spectroscopy of faint and distant supernovae. The James Webb Space Telescope will observe supernovae in infrared wavelengths, revealing different aspects of the explosions. Gravitational wave detectors will reach sensitivities where nearby supernova detections become possible. Advanced neutrino detectors will catch neutrino bursts from galactic supernovae, providing direct probes of core collapse physics. X-ray telescopes will map shock interactions in unprecedented detail. Radio telescopes will track long-term evolution of supernova remnants. Together, these facilities will provide multi-messenger observations across the electromagnetic spectrum and beyond. This multi-messenger approach represents the future of astronomy. No single type of observation can answer all questions. Photons tell us about material visible from the outside. Neutrinos reveal what's happening in the core. Gravitational waves encode information about asymmetric mass motions. Cosmic rays accelerated in supernova shocks provide another probe. By combining all these messengers, astronomers will piece together complete pictures of explosive events. Supernova 2024 GGI marks a milestone in this journey. It shows what's possible when automated surveys, rapid response systems, and powerful follow-up facilities work together. The early detection by ATLAS, immediate recognition of its importance by human astronomers, rapid approval of VLT time, and execution of spectropolarimetry observations within hours demonstrated the state-of-the-art in time-domain astronomy. Future events will build on this success. As systems become more automated and responsive, the time from detection to follow-up will shrink further. As more telescopes join global networks, coverage will improve. As machine learning becomes more sophisticated, interesting events will be prioritized more effectively. The combination of technological advancement and human expertise will continue pushing the boundaries of what's observable. Looking beyond supernovae themselves, the impact of this research extends to many areas of astrophysics. Understanding how massive stars die affects our knowledge of galaxy evolution, chemical enrichment, star formation triggered by shocks, and the formation of compact objects. It connects to cosmology through supernova distance measurements. It touches on fundamental physics through neutrino properties and nuclear reaction rates. The elements synthesized in supernovae enable the existence of rocky planets and life itself. Carbon, nitrogen, oxygen, and other biologically important elements are produced in stellar interiors and distributed by supernovae. Iron and heavier elements essential for technology and biochemistry come primarily from supernova. In a very real sense, understanding supernova is understanding our cosmic origins. This connection between supernova research and the human story gives the science broader meaning. We're not just studying distant explosions out of abstract curiosity. We're learning how the universe creates the elements that make up our world and ourselves. We're understanding the life cycles of stars and how galaxies evolve over cosmic time. We're probing fundamental physics under extreme conditions impossible to recreate on Earth. Supernova 2024 GGI, in the end, represents one event in one galaxy among billions. But through careful observation and analysis, it has revealed secrets about how stars die. It has tested theories and guided future research directions. It has demonstrated capabilities that will enable even more discoveries. And it has added one more piece to humanity's growing understanding of the cosmos. The questions that remain are numerous and profound. What determines whether a core collapse produces a neutron star or a black hole? Why do some supernovae fail while others explode successfully? What roles do rotation, magnetic fields, and neutrinos play in different types of explosions? How does the progenitor's evolutionary history affect the final outcome? These questions will drive research for years to come. Answering them requires patience, creativity, and collaboration across disciplines and national boundaries. It requires continued investment in telescopes, detectors, and computing infrastructure. It requires training new generations of astronomers, physicists, and computational scientists. And it requires maintaining the sense of wonder that motivates scientists to spend careers studying exploding stars they'll never visit. That sense of wonder, the human drive to understand nature, ultimately powers scientific progress. It motivated ancient humans to study the night sky and track the motions of stars and planets. It motivated early scientists to develop physical laws that explain celestial motions. It motivates modern astronomers to build ever more capable instruments and analyze ever more complex data. Supernova 2024 GGI, captured in those few critical hours after explosion, represents the current frontier of that ancient quest to understand the heavens. As technology advances and knowledge grows, future discoveries will push even further. But this supernova, observed in unprecedented detail at the moment of its birth, will remain a landmark event in the study of how stars die and how the universe creates the elements of existence.